Today I want to talk about a method Mark and I have developed to use spatial gradients information from to extract small-scale information from observation with spatially correlated errors. So we all know that that satellite brightness temperature is the observation type that has the biggest impact on atmospheric analyses and ensuing forecast. But these observations are still underused because brightness temperature errors can have significant spatial correlation. There are many causes to that: the correlated instrument noise or representativeness errors, and also the fact that there are correlation in the background state that are used in the observation operators. These are a few causes of those spatial correlation. But the problem is that the conventional assimilation algorithms that we use assume uncorrelated observation errors, especially in the spatial domain, because we do use interchannel correlation. And we pose that assumption because inverting the full covariance matrix is prohibited, is very expensive, and it's a bit difficult to estimate the real error correlation. Of course, there are some methods like the Desrosiers approach, but they are based on some assumptions that sometimes are quite strong, like the perfect B matrix. So it's common practice to spatially thin the observation or to reduce the error correlation between the remaining observations, which results in the loss of small-scale information. So our goal is to develop a practical assimilation approach to extract those small scales that we're losing from observation with spatially correlated error, but we still want to use a diagonal R matrix. So we still assume the spatially uncorrelated observation in the assimilation. So to test different approaches, I developed an experimental framework where assimilation experiments are performed in a simplified context to assess the impact of observation with correlated errors on analysis. So basically, it's pretty simple. It's a unidimensional periodic domain with a single dimensionless variable. The observations are available at every grid point, which makes sense because satellite radiances, like their resolution ranges from kilometric scale to about 40, 50, 60 kilometers, which is about the ranges we use for atmospheric model. Like in Canada, we have a 2.5 kilometer for our LAM, and our global was at 25. We're going towards 15 kilometers. So the scales are rather similar. So in my experiments, I set the background and observation error variance to 1, and I did test using several correlation functions, so the Gaussian, single and first and second order autoregressive functions, and the correlation length scales are defined with respect to the Eve folding scale. So the background error correlation length scale is set to 3 grid points, and the observation error correlation is varied from 0 to 4.5 grid point. So beware that most of the graphs I will show today are based on the worst case scenario, so the most difficult one, so that we can visually assess the difference between the methods. So I selected the Gaussian approach where the observation error correlation length scale is set to 4.5 grid points. So that's a case where the observation error correlation is larger than the background error correlation. So for all cases, I computed the true analysis error covariance following this equation here, where B and R are the true background and observation error covariance matrix, and REST is the estimated observation error covariance matrix used. So it's typically diagonal. And all the tests I'm presenting today employ the optimally inflated variances. So to be sure that we start with all the same mindset here, here I present the spectral variances of the observation error for the case where we have positively correlated errors. So we see that we have more energy at the large scale, similar to red noise. And when we make the assumption of uncorrelated observation error, it's like specifying the same value, same error value for all wave number. So by doing so, we overfit the large scales, which we see in the red, and we underfit the small scales. So this is why we often perform inflation, so that we can correctly fit the scale at which the background error has the most energy, so the large scales. But in the end, as we can see in blue here, we further neglect the small scales. We also often do some data thinning. So here we can see that from thinning, the spectrum becomes more flat, so we reduce the correlation between the remaining observation, but again, we're losing information at the small scales. So here I show some analysis results. So these figures are the spectrum of the analysis error for different value of thinning. So the black curve here is the perfect case scenario. So it's using all observation with perfect non-diagonal R matrix. So this is our benchmark that we were trying to approach. In red is the case where we are using a full R, so a non-diagonal R matrix, and in blue we see the results from using a diagonal R. So when we compare the red curve with the black curve, we see that going from left to right, the more we do thinning, the more information we lose at the small scales. And then when we compare the blue curve with the red curve, we see that the more thinning we do, the less impact so more we do thinning, when we do the assumption of a diagonal R, we have much less impact. So in the end, with more thinning, the impact of neglecting a correlation is reduced at the expense of losing scale at an increasing number of wave numbers at the small scales. So here, when we look at the bottom graphs, which represent the inflation factor, the optimal inflation factor, and the residual correlation between the remaining observation for different value of thinning. So in X, it's the distance between the assimilated obs. Is that a pointer? Yes. Okay, so we see that the more we do thinning, the less we need to inflate the variances, and that the inflation factor approach the value of 1 when the correlation approach 0.2. So this is consistent with what Liu and Desrosiers showed. However, we realize that when we look at the analysis error, so with optimally inflated diagonal R, the analysis is degraded slightly with thinning. So the more we thin, the more we degrade the analysis. So it's best to keep all the observation. And I think this is something I personally misunderstood from Liu and Rabier. And at first we were expecting to get an optimal analysis when doing thinning if we were having a correlation of 0.2 or less. And it makes me realize that it's better to keep all the observation if possible. So as I've shown, the thinning and the inflation both can prevent overfitting the large scales, but this is done at the expense of losing information at the small scales. So inspired by Jeff Sanderson's talk in Australia, we decided to try using spatial differences of neighboring observation to increase the weight on the small scales. So in a nutshell, the idea is to create a new observation set by computing the differences between neighboring observation. So the goal is to combine those thinned observation that as we were currently using them in our operational system and combine it with spatial difference observation, both with their tuned diagonal R matrix. And we're hoping to allow introducing complementary information at small scales. So again, this is the spectral variance of the observation error. So before we had something similar to red noise, but performing a spatial differential operator in the spectral space it's like multiplying the spectrum by the wave number. So we end up with a bell shape. So this is why we're expecting to have more impact on smaller scales using difference observation. I must admit there's a glitch in this graph because normally when multiplying by wave number 0, the value should be 0, but as I was trying to find a way to plot wave number 0 in a log plot, I introduced this glitch, so beware of that. So I want to show you the analysis results when assimilating those difference observation. So here in black again, it's the best case scenario, but in red, it's assimilating the difference observation with a diagonal R and with a non-diagonal R, and in blue, it's assimilating the difference observation with a diagonal R. So when we compare the red curve with the black curve, we see that it's identical at all points except at wave number 0. This is because we're assimilating spatial gradients. So we're completely losing the information at wave number 0. But when we use a diagonal R, we see that the impact of that bell shape I just showed you. So we're doing pretty well in the intermediate case, but we're underfitting the observation at large and fine scales. But when we compare that to what we were doing when we were assimilating all the original observation with the optimal inflation, we realized what I circled in red, that there is some potential benefits there. So the idea is to combine those, so the original observation to get the large scales right, and then the different subs to get the intermediate scales. So this is what I show here. So in red, it's the results from the original approach, and in blue, it's the combined approach. So we see that with the combined approach, we still do pretty well at the large scales, but we're able to improve the analysis error in the medium scales. So we have to keep in mind that we're neglecting the residual correlation that we have in the difference observations. So we still don't do super well at the very fine scale because we don't have information at those scales, or we underfit them. So here I present you it's more like an overall graph to present the results. So these are the analysis error, the standard error for different value of thinning. And in black is the case where I was using only the original observation, and in red it's the combined approach. So there are two things in that graph that we must look into. First is there is an overall difference. So we see that the combined approach provide a much smaller analysis error, so we're improving the analyses. But also we see that it's much less sensitive to the amount of thinning we're performing. So it can be sometimes hard to find the right amount of thinning in our system, but using the combined approach, we don't care much because it's not sensitive anymore. So before I conclude, I got a couple of take-home messages that I want to read to you. So I've shown that the necessity of using a diagonal R in our system at Environment Canada sacrifices the small scales. So we perform both inflation of thinning. We perform both inflation and thinning to give the correct weight to large scales, but in the end we end up losing the small scales because of that. And something I haven't shown in that presentation is that the analysis error is very sensitive to the observation error correlation function, whether I use Gaussian or first order. And the length scales, it's also very sensitive to the length scale. But something I learned from these experiments is that with optimally inflated diagonal R, the analysis is degraded with thinning. So we'll probably do some experiment to try to find the optimal inflation and reduce thinning as much as possible in our system. But in the end, what we aim to do is supplement the current methods with complementary information from different observations so that we can improve the analysis at intermediate scales while still using a diagonal R. So the big drawback of that method is that now we will have two parameters, two inflation factors that we need to tune experimentally. But in the end, we expect to reduce the overall analysis error and also to provide a good fit to observation, not only at large scales, but also at some intermediate scales, which may help for convective scale forecasting systems. And something I didn't have time to cover today is that I've shown you that the analysis error is less sensitive to the amount of thinning, but it's also less sensitive to the structure and the length scale of the error correlation. And I think this is very important because we don't know what the true error correlation, observation error correlation look like. And it may be flow dependent because of the background states that we're using in the observation operators. So having less sensitivity to the structure and the length scale of the observation error correlation could be a pretty good asset in the future. So that's about it. Thank you very much.
Great, thank you, Joe.